Hey, what's going on, guys? Comicgeekins here. So we are continuing our work on developing a hex editor, an application allowing to input raw bytes to the certain location within the random access memory, with an idea to code in machine codes, believe it or not, under the GameOS. So one of the core parts of this editor is actually a viewer, because every time we type in the byte and before encoding the byte and storing the byte, it's really a reasonable thing to consider just to print exactly 512 exactly 512 bytes of the memory. And just to recall from the previous part, so it would leave here at the address of hexadecimal 500s, so the very first address available in the real mode, in 16-bit real mode for x86 processors. Okay, so first we'll provide the viewer functionality, so we could just print all the 512 bytes and the corresponding addresses to those bytes, and then we'll go for actually filling those bytes. Okay, and the very first and one of the most initial routines to consider is to convert the byte value to a string, to an ASCII character. So in order to make it possible to see the bytes as in hexadecimal format, hence the name of this hex editor, hex viewer, doesn't matter. So we want to see what is known as the hex dump on the screen, and in order to make that possible, we need this tiny little routine converting this kind of like byte values to the ASCII characters. So you can see like 7, 5, FF, AB, CC, D10, and so on. So just like the byte values. Okay, so without further ado, let's actually start coding this routine, and then probably at the very end we'll add some more core variables here, because the next video is going to be quite pretty time consuming, because of the entire print memory routine is going to be implemented there. It takes time to explain all the tiny little details on that. So yeah, let's just go step by step. And the routine we're going to be writing is going to be converting. So convert nibble. So what the nibble is the half of the byte. Just say half of a byte. So 4 bits literally. Convert nibble to ASCII characters. Okay, and let's just call it hex to ASCII, like this. And this is going to be a procedure. So let's say procedure to convert nibble. Okay, so in order to make it work, we need to make sure that we have a nibble value in AL register. Okay, so we want to say compare AL and with a 10. So now we need to distinguish between the digits and the letters. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then A, B, C, D, E, F. So this is known as the hexadecimal system for numbers, numeric system. So distinguish, hope I spelled it correctly, sorry guys. Yeah, it feels like. Okay, so distinguish between digits and letters. So I want to say, so if jump less, so if AL contains the value less than 10, then it should be converted to a number. Otherwise, it should be converted to a letter. Okay, so the number printed or a letter printed. In this case, let's say jump less, jump to the digit, and this is going to be a label. And so here we want to convert to digit. Okay, let's say not convert to convert convert digit. Okay, and it's probably not the most efficient way of doing things, but it works. And jump greater or equals to convert letter. Okay, so convert letter. Okay, and now here is the digit label. So here we can simply say add to AL. We want to add, and here is the hack. This is also done in C to convert integer to the char, to the character, right? So we can just add the constant of this 0 character. And just to give you an idea what in particular this value is, this value is, so we just say, whoa, cool. Okay, so 0 and char code add. So this is 48. So instead of this, instead of plus 0, we could have say like plus 48, or even convert it to hexadecimal, but it's really way more clear to see, to make it like this. So here we want to convert integer to character. Okay, that's pretty it. And then we want to print it, so I say jump to print. Okay, and now we want to process the letter, so process, letter, and so here go print, and print it. Okay, and here we want to add to AL, we want to add A, but not just A, because otherwise it would be just like 0, and we want A to be equal to 10, because A is equal to 10 actually in hexadecimal. So we need to say minus 10 here. I'll demonstrate how this works in practice, so it gets more clear after that, I hope. So the same thing, convert integer to character, and here let's say digits 0 from 0 to 9, and here we have the letters A to F. All right, so here we go. Maybe even make it like this. Okay, and again, like jump to print, and finally we have the print. Let's call it print nibble. Print nibble. Actually, it's better to say print nibble, because this is exactly what we're doing here. We're printing a single nibble, which is the half of the byte. Print nibble. Yeah, go print it. All right, and here we just need to say move to AX the value of 0x0e, which is the BIOS code to print a character. Okay, and then call the interrupt hexadecimal -10, which actually allows to print this, it. So print character to screen. And that's pretty it, guys. That's pretty it. Very simple. So from now on we can actually test it. Yeah, but before anything else, you see, like, we have this edit bin appeared, which is not really that great. So let's add this to list bin and edit bin. I don't really need this here. And if we exhaust the 512 bytes, well, we won't, but even if we could do that, it won't get compiled, and like it won't get assembled and give us an error message, a warning, and that's just not going to be working. So no worries about that. Yeah, and now let's open the terminal and run, and yeah, it just deleted this edit.bin, which is great. Okay, and list, so we have the edit. So whoa, why do we have Tetris? Okay, this is a bit strange to say at least. Hold on. Okay guys, I just figured out what this is happening is because we didn't return from the function, which is absolutely essential obviously, because otherwise it just goes and executes whatever we have further on. So yeah, now it should stop. So list is okay, edit. Okay, now this is getting really interesting. So yeah, this is really getting interesting. So what's wrong? Control X. I mean, this is strange because it was working in the previous part. So okay, so definitely something wrong with this code. Oh, or not. This is a little bit strange. I'm just wondering if I stuck it here for now. You must be kidding me. Okay, hold on. Okay guys, sorry, just this happens quite often. I just didn't see the error, and that's the reason why it works so horribly. So 26 and 28, something wrong there. So 26, what is wrong there? Invalid opcode and operands. Oh, oh my god, what have I done? There shouldn't be, yeah, colons, obviously. Okay, so we stuck forever. Okay, let's just jump back to the shell. Shouldn't be doing anything yet at the moment. Yeah, okay. At least doesn't start Tetris now, which is already a good idea, a good thing. Okay, and before that, so now let's go for a bit of a test. So we need to, well, let's define some test byte here. So test byte. Okay, let's go for a test byte. I will just demonstrate the technique that was supposed to be used in the next video, by the way. Yeah, so let's say define byte, and let's give a digit like, I don't know, 5 and A. Okay, so this is our byte. Save. Yeah, and it's pretty it. So now let's say move ASCII to test byte. So now ASCII register points to the address of the test byte here, and if I say load single byte, so yeah, it's a bit of a test routine, but okay. So point, we'll get rid of this later on. Point ASCII to test byte, load value at ASCII to AX. To AX really, or AH? Hold on. Okay, so since we have a byte, right, not a word, that means that it gets stored not in the AX but in the, well, actually push to AX, but we only need AL. So now we need to extract two nibbles from the AL register, so the lower part, the 8-bit part of the 16-bit AX register. So let's temporary store AL value into the CL register. So just to store it somewhere. So here I say temp store AL to CL. Doesn't matter, it could be DL, but it's just in my implementation I'm using CL. Okay, and now to extract the first digit, we need to bitwise and the AL with a constant of hexadecimal F0. Now what this does, so here just say extract first digit or nibble, digit or nibble. So what this does, I just show this and probably get rid of it. Yeah, and anyway, this would get deleted, so it's okay. So this value in binary, this is gonna be like 11110000. Okay, so if we bitwise and this value with AL, right? Then we have that's the way how we can extract the first nibble, and then we just need to right shift this to 4 kind of like this 4 bits, and we will have the first nibble or the first digit. So shift right AL 4 and so right shift 4 bits, and this value turns into this value, and ones is this bits, like with 1 it represents whatever digit we have. So here we just right shift first nibble 4 bits, shift first nibble 4 bits to the right. Okay. Yeah, and now we can actually call. So now we can call hex to ASCII. And if I did everything properly, it now should print 5 to screen. So let's actually figure out if that is gonna be the case. So edit, and yeah, for some reason it's not working properly. Oh, that's because, hold on a sec, that's because I didn't put anything to, no, hold on a sec, this should be initialized. Okay guys, sorry, just as always, as it always happens, it's just a little typo, so just get rid of my debugging stuff here, and restore everything. Like this, and we can even clear the direction flag, which is not essential here, but yeah, by the way, here we don't even care about increment or decrement ASCII because we read the only byte, yeah, so we don't care about this. So here, obviously not AX, but AH. So AH holds this teletype mode for BIOS, and AL takes the actual character that we want to write to screen. So edit, and we got 5, and which is true because here we have 5. Okay, and now how to make another. So here we just want to print nibble. Okay, print first nibble to be exact, and now we want to restore the value, restore byte value from CL back to AL. All right. And now we bitwise and AL, but with this constant. So F now goes, so extract the second, oh, sorry, Control Z. Now we want to extract the second digit or value. As let's say the second nibble because it might be either a digit or letter. Extract the second nibble, and this is how it works. So hexadecimal 0f, in binary we'll have 000 and 1111. So it's the same, but we don't really need to right shift anything because we already have this kind of right on the place, and we don't care about. So here we might have whatever. So here we might have whatever, but it doesn't matter because only this is what we need. So as long as we bitwise and the AL with this constant, we just strip this line. So like here we would be having zeros, and now we just pass this to the call hex to ASCII. So here we want to print the second nibble. All right. So yeah, let me just have a look at the explanations. Okay. So this, yeah, just to give an idea, bitwise and with AL. Okay. Okay, which might be like whatever. Okay, so I hope it's clear. Yeah, I think this might be just okay. Yeah, and let's have a look at the output, at the final, the final output. All right, so edit, and here we have 5a, which is exactly the value of the byte that we have here. So let's try FF, for instance, and edit. So now we have this FF, and whatever value I put here, like I don't know, like 61, right, which should be the hexadecimal value of the character A, by the way, should be, or if I didn't miss anything. Okay, edit, and we have this value. So now once we got capable of printing a single byte, nibble by nibble, we're now able to print all the bytes basically. So the only thing left here to do so is just to point SI to not to the test byte, but to the actual location in the memory, where exactly we're supposed to be reading our bytes from, and that location is 500 hexadecimal, because that's where we decided to keep our 512 bytes chunk of the data that where we're supposed to be writing our machine codes in bytes using hexadecimal numbering system, and then we would be able to run that. So that's pretty much it. Yeah, and what else? Yeah, so now this is it regarding the tutorial, but I just want to make some sort, so we don't actually want to do this sort of a thing, so this can be removed, hex editor, so we don't need this one. And now I want to preserve some variables for the next tutorial because it takes time and it needs some explanation, and the next tutorial would be long on its own because it contains quite pretty lots of things to do. So we will need, so the map, if you've been watching my video on coding in machine codes, it's like around 1 or 2 videos ago before this one, you can check the series playlist on coding the GameOS and software for GameOS as well, which we're doing in this series, and there would be a video, and this is how the layout is going to look like. So probably can, so this is the layout. So this is going to be hex dump, and how this is going to be looking. So we literally take, so the addresses from hexadecimal 500s, and then 1 byte, 1 2 3 4 5 6 7 8 9 10 11 12 14 13 14 15 16 and doubled. So we have 32 bytes. Okay, and if we have 32 bytes, we need only 16 lines to encode the entire sector. So here we will have 0 500 and yeah, now this is a good question. So 32 in hexadecimal, it should be 20, but let me check that. So I'm going to hexadecimal. So yeah, a bit of an explanation of the layout here, guys. So for those interested in the details, you may keep watching. I will appreciate that. So just go into decimal and 32 bytes. That's the offset to like 32 bytes offset. So the next address, I'm just trying to calculate 500s in hexadecimal plus 38 bytes in decimal. But first we need to convert this to hexadecimal. So hexadecimal should be 20. Okay, and now 500s plus 20 should be 520 plus 20. Okay, 520. So here, copy, then hexadecimal 540 respectively, then hexadecimal 560. Okay, hexadecimal 580, and then we need to be careful because 500s, and now we need to take, so let's say plus 20, just checking out 20. Okay, and then plus 20 is gonna be 5A0. So here we need to say 5A0. Okay, then it will probably be 5C0, but let's check that out. Plus, sorry, no, 5A0 plus 20 equals 5C0. Yeah, 5C0 and 0x5. Now it should be 5E0 plus 20. Yeah, 5E0. Okay, and plus 20 and 600. So 0x 0 600. Now it gets a little bit easier. So add in 12 is just like in decimal. So 0x 0 620 and 0x 0 640 and 0x 0 660 and 0x 0 680, and we're almost done. So plus 20 plus 20 plus 20 and plus 20 here, 6A0. So 0 6A0. Oops, sorry, 6A0. Then it should be 6 E0, no, C0 first, then hexadecimal 6, E0, and let's check this out, plus 20, C0 plus 20, E0, and let's count if we need any more. So we need 16. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, and this is it. And now we have exactly 512 bytes here in hexadecimal that would be printed in hexadecimal. I don't provide spaces either like this or like this, just because it doesn't fit the 80 characters width of the real mode, video mode. Basically, there is only 80 by 25 characters. It's pretty much it. So we don't fit the entire. So this is the only way how we can fit the entire screen width, and might be not the very most ever kind of comfortable way of doing things. But guys, again, like, we're living in a 512 bytes world in within this GameOS, so let's really go hardcore. Okay, so if we take 32 and multiply by 16 lines, so we have 32 bytes per line and 16 lines, we have exactly 512 bytes. So just to demonstrate you that, so this is done in decimal, and we have 32 bytes per line, and if we multiply by 16, we have 512 bytes, which is exactly how many we want. Alright, and now we need to store all of these values as the variables, like for printing strings. So to print this, this is the output. I've just drafted the output that our hex editor is going to be making every next iteration of the edit loop, because once we've entered the value, we really want to see how this is going to be represented, right? And another reason is to have the variables like for an offset. Okay, so we're gonna be keeping track of the lines and like the columns and the rows, and in order to increment the address by row, we're going to be using the BX register serving as an offset. So without further ado, let's actually define these variables I'm talking about, and then it gets clear in the next tutorial. So line 1 define byte and ends with a 0 terminating character, so I want this one, and I also want this. Yeah, and probably I can even go for no, this takes too much space, so we would better, yeah, we would instead just programmatically add that space, and copy, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16. And also we define the lines, and in this case define word. This is important because we are going to be adding the BX, and to make it fit the size we need to make it in words. Okay, so here we have line 1, line 2, line 3, line 4, line 5, line 6, line 7, line 8, line 9, line 10, line 11, line 12, line 13, line 14, line 15, and line 16. Okay. We don't need the 0 terminating character here because we would be asking whether the row counter has exhausted the value of 32, not 16, because it would be like iterating like 2 bytes every time to get the proper offset. So yeah, just like that. Okay, what else? And yeah, the reason why to use the word here, because we need, so this here we have an address, and here we have an address, and addresses are stored in 16-bit, not the 8-bit. So that's the reason, in order to store the address, so literally what we do here, so line stores the addresses of these variables, and to store a single address we need a word. We need 2 bytes, not one byte. That's the reason why. That's another reason why to use word here instead of a byte. Okay, so variables. So yeah, this is self-explanatory. So I can, well, new line is self-explanatory. These lines are also self-explanatory, and also we want to have, I don't know how to call it, read address apparently. So yeah, let's call it read address. Read address and define word as far as we are defining the addresses. And here, yeah, I didn't yet. So yeah, I also need to. Didn't want to go, but 4, 6, 8. A0, C0, E0, then 600s, then 600s, 620, 640, 660, 680, and then 6A0. Then 6A0, then 6C0, and finally 6E0, just like we have here. Okay, and now we just use them here, copy, paste, copy. I will double or even triple check this later on, just to make sure that the memory dump matches the real memory dump. For otherwise, it's going to be a real disaster, right? Okay, it's better, probably faster do it by hands. Okay, 560, 0x 0580. And 0x 0 5A0 0x 05 C0. Okay, and 0x 05 E0. And now here I can just do the same, but with all the 6, right? Yeah, just the next one goes the 600s, and that's pretty it. That's pretty much it. I always remember Dr. Pi when I say pretty it, because he kindly told me that it's wrong to say so, that people should say that's pretty much it in English to sound like a native. Okay, so yeah, I really hope it's okay. If not, the further tests would actually show this stuff to us, guys. Yeah, and for now we have this sort of a thing here. So yeah, I just keep I just keep this test stuff. I'll get rid of this test stuff in the next video, and we will also have the variable called the write address, and define word 0x00. So this here in this variable we're going to be storing the user input responsible for the address to point di to. So di would be pointing to either here within the range from here to here plus 20 in hexadecimal or 32 in decimal, and it's like placing a cursor, let's say, to a certain position, so literally pointing. So di register would be storing the pointer to the certain memory location, and then using this stosb command, store single byte, right? We're going to be writing a converted from the user input ASCII characters to the actual hexadecimal representation of a byte. That byte would be stored to where di is pointing using this stosb command. That's how it's gonna be working. I'm just wondering. So let's say instead of variables, let's say that would be the variables here, right? But here I just want to say print addresses. So this is how it's going to be used, print addresses, and here we want to map printed addresses, and here we have read addresses references references for addresses to read from, or pointers to those addresses. That might be the way to talk about this as well. And this is the user input of to store reference address to write bytes at. Okay, let's just say address to write bytes at, and here let's just say addresses to read bytes from. That's more simple, and as Dr. Pi taught me one day, it's better to do things simple. Addresses to write bytes at. Okay, addresses to write bytes, let's say 2. Might not be the best ever. I forgot how this part of the speech is called, but you got me. Okay, and fill with the trailing zeros. And probably can make it like this. Okay, alright guys, so we're almost there. This test stuff, let's put it here for a while. I'm not sure we're gonna be having any more variables. Yeah, let's run the code at, oh my god, what has just happened? Whoa. 67. Oh, yeah, we can do, yeah, oh, I'm sorry, in assembly we can do this, like so. Alright, so here we have a hex dump. That's pretty much it. Okay. Alright, so it all looks much better. Okay, probably, yeah, I think this is okay, good enough. So let's try to run again, no warnings, no errors, edit, and we have 61 from the so whatever, literally whatever we have here. So yeah, the difference would be instead of referencing this local variable, which from the machine code's perspective, this is just exactly the same address as the one, say here, or wherever in the memory. It's just a matter of how to calculate that based on the segment we currently are, where the data segment is pointing to be exact, and the offset from the data segments where it points to, plus this bytes, and up, and then up here, wherever. Okay. Yeah, I think I can stop here, and yeah, in the next part is going to be way more exciting compared to this one. In the next part, we'll finally create a routine to print this memory dump to screen. That's pretty from my side, guys. That's pretty much it from my side. I'm sorry. So I hope you learned something interesting out of this tutorial. Hope it helps. So until the next time, and take care.